Okay, so the voltage-gated sodium channel. This goes along with understanding the action potential. I just wanted to break up the content a little bit more. So the action of this protein is really important for the action potential. So I want to start with looking at it at rest. Here is that same kind of graph, millivolts on the x-axis. This would be time. And at rest, and then here's our threshold, minus 55. At rest, what is the voltage-gated channel like? It's closed. This is what it looks like when it's closed. When we reach threshold, it opens. That's it. It opens. When we reach the top of our action potential, I told you that they close again. It's actually an inactivation gate that's going to close them. This allows for it to be a quicker closing. What else is happening at this time point up here? Potassium channels are opening. Voltage-gated potassium channels. What causes voltage-gated potassium channels to open? This positive voltage here. Both the action of the sodium channels being closed and the potassium channels being open causes the membrane potential to go back negative again and actually overshoots and goes hyperpolarizes. And so K plus leaving the cell, the two gates then reset. So now the sodium channel is ready to go again to be activated with the next stimulus that is large enough. So here is a walkthrough of the channels only. Pay attention to the gates opening. Here's our resting membrane potential. A local current causes voltage-gated sodium channels to open. If threshold is reached depolarization to threshold, the local current causes voltage-gated sodium channels to open. That causes a rapid influx moving in of sodium ions that causes this rapid depolarization up to here it's plus 10, ultimately plus 30. This is a positive feedback mechanism. The opening of voltage-gated sodium channels causes more depolarization, causes more opening of voltage-gated sodium channels. Positive feedback. Okay, we had that already. Right? Then at the top of that loop, so the top, we're at plus 30 here, we have inactivation of the sodium channels and activation of the potassium channels. That's going to cause, there's that inactivation. Which way does potassium move if the channels are open? Out, right? That's down its electrochemical gradient. Potassium is going to move out. There's more of it inside the cell. It's also positive inside the cell now. How does this change membrane potential? It's going to make it more negative. Sorry for that overlap there. That's going to bring us back to minus 90, hyperpolarized. Then we can establish our resting membrane potential again. Okay, so this is another walkthrough. I'm not going to walk through this right now. This is the same as what I've been over twice already. This is a nice figure I just wanted you to have that summarizes all of this in terms of the channels that are open or closed in each state of this action potential. You should practice by drawing this yourself, like I did in that first video, but you could draw beautiful channels and make it even more beautiful than mine. I'll come back to these terms up here, the refractory periods, in the next video. Okay, so what we've just done is label or interpret, be able to do both, a voltage versus time diagram of the action potential with the ions involved in each phase, direction of their movements, and these special terms used to talk about the membrane potential. These are some of the most important channels involved in the action potential. So please draw this out for your own practice as well.